What we're going to be looking at today is we're going to be looking at how do we do Laplace transforms for periodic functions. The most common periodic functions that we know of are trigonometric functions. And we'll do an example of one of those, even though we already have some basic Laplace transforms for trigonometric functions. We'll also look at Laplace transforms for periodic functions that are not as obviously periodic, but that actually show up a lot inside of, say, for example, circuits or logic circuits. And so this particular technique is going to be useful for being able to work with those because it really kind of simplifies things. This should be a pretty short video as we're only going to go through a couple of examples and there's only a single equation. If you want a proof of where we get that equation from, I'll actually be putting up a video at a later time. So let's actually start by defining what it means to be periodic. So this definition, f, defined on an interval 0 to infinity, is going to be said to be periodic with a period of big T if big T is the smallest positive real number that satisfies this equation. F of t plus big T equals f of t for all t greater than or equal to 0. Now big T is going to end up being a constant value, and then it's going to end up being our period. So we'll take an example. Let's say, for example, we have f of t is equal to cosine t. Now what we know is that cosine of t plus 2 pi equals cosine of t. And we can, in fact, multiply 2 pi by any amount that we want, as long as it's an integer amount, and we're going to get back whatever cosine t is. So cosine is periodic, and its big T is equal to 2 pi. And we'll look at that one in just a moment. Now, if we have a periodic function, then we're going to define the Laplace transform for that periodic function utilizing this equation, okay? And that's L of f is going to equal 1 over 1 minus e to the negative s big T times the integral 0 to big T e to the negative s little t f of t dt. Notice, again, t here, that's our period. So in our previous example, that would be like 2 pi, for example, all right? And so consequently, this thing out here, that actually is a, is a function of s, all right, and not in fact a function of t, because that's a big T. So let's take a look at an example. So now let's go and find the Laplace transform for cosine t using this periodic Laplace transform formula. So we're going to find L of cosine of t, and we know that big T is equal to 2 pi for cosine. Now this is going to end up equaling 1 over 1 minus e to the negative s times 2 pi times the integral 0 to 2 pi e to the negative st cosine of t dt. And what we'll do now is we're going to utilize an equation from our list of equations. So we got 1 over 1 minus e to the negative 2 pi s. Okay, and that's going to be 1 over, and our a is going to be negative s, so this is going to be negative s squared plus 1 squared e to the negative st times, and we'll get negative s cosine t plus sine t, rather minus sine t, evaluated from 0 to 2 pi. Excuse me, that's actually plus sine t. And now we'll evaluate from 0 to 2 pi, so this is going to equal 1 over 1 minus e to the negative 2 pi s. I'm going to pull out my 1 over s squared plus 1. And then I'll have e to the negative s times 2 pi times negative s cosine 2 pi. So cosine 2 pi is going to end up being negative 1 plus sine of 2 pi plus 0 minus e to the 0 times, and this will be negative s times cosine of 0, so that's times 1 plus sine of 0 plus 0. And then we're going to go and do a little algebra, or rather a little bit of equations. And so this then gives me 1 over s squared plus 1. And I'm going to move in, I've got 1 over 1 minus e to the negative 2 pi s times, and then this is going to be s e to the negative 2 pi s, and then plus s. And this is rather negative s e to the negative 2 pi s. And when I rewrite that, I get 1 over s squared plus 1 times 1 over e to the negative 2 pi s times s times 1 minus e to the negative 2 pi s. And what we can see is that these are going to cancel out, okay? And we're left with s over s squared plus 1, which is exactly what we expect to have with our Laplace transform. So what you can see is you could actually get the exact same thing utilizing this periodic transform as you would get with the conventional Laplace transform. Let's do another example. So now what we've got here is we've got a function that's piecewise. So we're going to find the Laplace transform for f, and f is going to be negative 1 when t is between 0 and 1, and 1 when t is greater than or equal to 1 and less than or equal to 2. And then we're going to see that it's going to be defined as periodic because we've got this here. F of t plus 2a equals f of t if a is an integer. What this does, this right here, that's going to end up being our big T. So big T is going to end up equaling 2 because every 2, we're going to get the same function. So consequently, we can use our periodic function. Now this is different from the cosine. Okay, what this one is doing is it's basically a constant function between negative 1 and 1. So what we'll do is we'll actually set up our equation utilizing our periodic function equation. So we got 1 over 1 minus e to the negative 2s times the integral of 0 to 2 e to the negative st f of t dt. And I remain having with f of t dt because we're looking at a piecewise function. Now what I'll do is I'll separate it out. So I got 1 over 1 minus e to the negative 2s times, and this will be the integral from 0 to 1 e to the negative st, and then we'll multiply by negative 1 dt, and then plus the integral from 1 to 2 e to the negative st dt, because it's 1 from 1 to 2. This will give me then 1 over 1 minus e to the negative 2s times, and this is going to be negative 1 over s e to the negative st, evaluated from 0 to 1, plus, and then we'll get negative 1 over s e to the negative st, evaluated from 1 to 2. We'll go to our evaluation. This is going to give me 1 over 1 minus e to the negative 2s, and then 1 over s times e to the negative s minus e to the 0, plus negative 1 over s times e to the negative 2s minus e to the negative s. That gives me 1 over 1 minus e to the negative 2s times 1 over s e to the negative s minus 1 minus 1 over s e to the negative 2s plus 1 over s e to the negative s. Combine our terms, and we get 1 over 1 minus e to the negative 2s times negative 1 over s e to the negative 2s plus 2 over s e to the negative s minus 1. And there you go. So it actually simplifies things quite a lot because we don't actually have to evaluate over the entire period. And it gives us a really kind of clean function that we can work with. Pretty simple integration by parts for the most part. Okay, so that finishes up this mini lesson on working with periodic transforms. Remember, anytime you get a function in which the function is periodic, that is that it gives you the same function over and over and over again for some big T, we can utilize this particular formula and it can simplify things quite a bit. This is Dr. George Sweeney, and I want to thank you for watching my video. If you found it helpful and you liked it, go ahead and click the thumbs up. If you want more of these videos and you want to get my updates, please click subscribe. If you have any questions or you just want to say how much you really enjoyed the video, go ahead and leave some comments. I do read and respond to the comments.